Hey everybody, before we start to do the word problems for this chapter, I'm going to go over some applications to kind of motivate you to regarding these equations. So this is from the respiratory program, so I'm just going to go over these kind of quickly and not in a lot of detail, but just so you can see what's happening. So we talked about gauge pressure. So gauge pressure you can see here, you can use that to talk about the oxygen tanks and the pressure. You can look at it on the picture on the left there. That is going to be, you can see the tank is measured in PSIs or pounds per square inches. Also, you can use gauge pressure to describe what's happening inside these rebreather masks. You have, if the pressure on the outside is bigger than the pressure on the inside, then the mask will be deflated. And vice versa, if there's too much pressure on the inside, then the mask is going to get inflated. So you can control that by knowing the gauge pressure. Next, you have these flow rate devices. For example, here, you can see that this pipe here, there's these two small nozzles. So the smaller nozzles means that the air is going to flow faster through the smaller nozzles than through the sections that have the big areas. And if you notice there, the units are in liters per minute. You have another device where the nozzle size affects the flow rate. You can see you have I don't know if I can show it to you here. Oh, I might be able to use this. Oh, excuse me. Yeah, I'm just going to talk through it. So the size of the nozzles there are going to affect the flow rate. Also here you can see that this nebulizer, you have different size nozzles, and the bigger the area, the slower the air is going to flow. The smaller the cross-sectional area of the nozzles, the faster the air is going to flow through. And if you look at here, you look at the bottom right there, L per M, I believe that means liter per minute of oxygen. So that's going to be a flow rate. Another example here, flow rate, so small nozzle sizes, air is going to flow fast. And more of the same here. Different nozzle sizes are going to make air flow at different rates. And then you have devices that mix multiple equations. For example, this rebreather mask. The size of the nozzle is going to affect flow rate, but the bag itself is going to control how much pressure, the pressure at which the person receives the air or oxygen. Another example here, these recitation bags. Two things you have to take into account: the pressure on the outside versus the pressure inside the bag. That's going to be the gauge pressure, and then the rate at which the person receives the air, that's going to be the flow rate. And we talked about this one before. The smaller the nozzles, the faster the air is going to flow. And you can see here again, you have a different set of nozzles, and those will affect the flow rates. Everybody, this is going to be our first word problem for chapter 13. So here we were asked, what is the pressure 12 feet below sea level? So we're only given one number here, 12 feet, and we're trying to find the pressure at the bottom. So go ahead and pause, try to solve it yourself, and then once you're ready, go ahead and unpause. So let's write down what we're given. We're given a height. So let's just call that H, or let's go ahead and call it Y. 12 feet. And we're trying to find the pressure at the bottom of the ocean. So the picture looks like this is the ocean here, surface of the ocean. We're trying to find the pressure down here. Okay, so let's see what we need. Let's just consider well, first, actually, let's go ahead and convert the height into meters. So this is 12 feet, and we want to convert that into meters first. So you have 12 feet, and let's convert that to meters. So feet on top here, feet on the bottom, and we're going to meters. And when you look up your conversions, you'll find that 1 meter equals 3.3 feet. So the height then in terms of meters is going to be 3.6 meters. And the equation that we're going to use for this one is that the pressure at the bottom of a fluid is going to be the density of the fluid, or in this case water, multiplied by gravity, and then multiplied by the depth down, or in this case here, the height down. And so here we can just plug in. So the pressure at the bottom is going to equal the density of water, which is 1,000, times gravity, 9.81, and times the height in meters down, so 3.6 meters. And that should give you 3.5 times 10 to the 4 pascals. Now try this one. We have, so let's see, we have a 2.6 newtons of force is applied to the large end of a syringe, and that syringe has the large end has a diameter of 3.3 centimeters. And we want to find the force on the fluid at the small end of the syringe that has a diameter of 2.7 millimeters. So go ahead and pause now, try to solve this, and when you're ready, unpause. All right, so let's write down what we're given. So we have 2.6 N, so that's going to be a force. And we have a diameter, let's just call it D1, so let's call that one force F1. And so we're given a diameter of 3.3 centimeters. And we're trying to find the force on the other side, and we're given the other diameter 2.7 millimeters. So let's try to draw a picture for what's happening here. So you have kind of a tube system like this. You have a large end and a small end. Actually, let's make it more accurate. So this is for a syringe. So for a syringe, it's this way. So you have a large end of the syringe. And then you have the small end of the syringe. So the large end of the syringe has a diameter D1. And the force on the fluid here is F1. And then the small end of the syringe has a diameter D2. And we're trying to find the force on the small end of the syringe, F2. So what we need to do is first, let's convert those diameters into radii. So diameter 1 is 3.3 times 10 to the minus 2 meters. So radius 1 is going to be half of that. So that should be 1.65 times 10 to the minus 2 meters, because the radius is the diameter divided by 2. And so diameter 2 is equal to 2.7 times 10 to the minus 3 meters. And so radius 2 is going to be half of that, and that's going to be 1.35 times 10 to the minus 3. So now we have the radii. So the equation that applies to this setup here is the force on the large side, so F1 over A1 is going to equal the force on the small side divided by the area on the small side. And in this case here, in both of these pictures, the area is a circle. So we're going to use the equation area is pi r squared. So the equation is going to become force 1 over pi times radius 1 squared is going to equal force 2 divided by pi times radius 2 squared. So we can simplify this sum. There's a pi on both sides, so let's go ahead and cancel that. And you get that force 1 over radius 1 squared equals force 2 over radius 2 squared. And, well, let's just try to keep it consistent. So we're keep on using a variable. So we're trying to find F2. So let's get F2 by itself. So we're going to multiply this side by radius 2 squared. And we'll multiply this side by radius 2 squared, so that these two cancel. And you're going to get that F2 is going to equal force 1 multiplied by radius 2 squared divided by radius 1 squared. And so the force on the small side is going to equal force 1, which is 2.6, times radius 2, or the smaller radius, which is 1.3, 5 times 10 to the minus 2, 10 to the minus 3, excuse me. and all of that gets squared. And then also divided by radius 1 squared, which is 1.65 times 10 to the minus 2 squared. And this should give you 0.017 newtons.